And on the audio, probably was on anyway. All right. So yesterday we talked about differentials. We looked at 2 to the x. And I wrote it as 2 over 1 to the x to give you a little feeling for this function. We talked about 1, and then 2, and then 4. And we could have gone in the other direction, a half, so on and so forth. So let's just go back to the general shape. Let's give you a generic exponential model. All right, let's just say we have, let's do this. And let's do this. All right. So I guess the intellectual question I'm going to ask is, what's the inverse look like? Pause the video, give it some thought. Going to keep going here. So when you do an inverse, you're switching the x's and the y's. So if this is a y equals, and it's a horizontal, then it becomes an x equal on the vertical. If this is a horizontal, 1 to 3 to 9, maybe, I'm trying to say that that's 3 times that, that's 9 times that, then the same thing's going to happen over here. 1 to 3, about 3 times the size, to 9, 1, 2, 3. All right, and we're going to get a graph that looks like this. And over here, we're going to get a graph that looks like this. Let's examine it a little more carefully. Let's actually give this a name. Let's give it 3 to the x. All right, and if we look at -4, I get 1 over 81. If I triple that, I get 1 over 27, 1 over 3, 1, 3, 9, 27, etc. And this is just going up by 1, so that's -3, -2, -1. This is 0, 1. Did I miss one somewhere? So that should have been, yeah, I missed a 9th. I'm not going to stop the video here. I missed a 9th, but you get the idea. Over here is the asymptotic behavior where we're getting things like 1 over 81, 1 over 27, 1 over 9, 1 over 3, so on and so forth. So, you know, the mathematicians would say the limit as x goes to -infinity of the function 3 to the x is equal to a 0. And I think that's where we're headed. 1 over 81, 1 over what, 343, I think. Right? I hope you can see we're heading to 0. Now, the point of this intellectual exercise is if you have log base 3, you've got your differentials. This is really 3 over 1. And how do we count on the x-axis? We generally count from 0, 1, 2. We count from left to right because that's where the numbers are getting bigger. It's easier to move in that direction. And the y-axis, 0, 1, 2, then we count from below and go up. So this is my first differential, 1 unit. That's my next one, 3. And then 9, and so on and so forth. And, you know, we can make these more complicated, and I think I will in a second. But I just wanted to show that you can seem like people, you know, made some real gains yesterday when we talked about the differential is the base of your exponential function. So therefore, you can do the same thing for bases with logarithms. You can get a feel. All right. Now, of course, they get a little more complicated. And so let's do one that's a little more complicated and see if we can get the inverse of it without having to do it analytically, but we'll do it graphically and then validate it analytically. Symbolic, we'll do the inverse operations. But let's just look at a generic y equals. How about 10 times 2 to the x minus 1900 over 50 plus 7. So dotted line, y equals 7. We have a 2 to 1 differential that's going to get multiplied by 10. So I really have 10 units of change and then 20 units of change. I can see that that happens every, say, 50 years, so there's 50 years between these. Which means that in another 50 years, I'm going up 40. Well, it's not double. It's more than a marker length. So somewhere up in here. Okay, and then we can see the trajectory. All right, so let me do the inverse. Well, first I got to get 1900. Gets me 17. This one here is 1950. Should get me 27. And then in another 50 years, 2000. Should get me 40 more. And that's 47. All right. So what's the inverse of y equals 7? Well, it's too easy to do an inverse from this. So let's get the inverse by switching our x's and our y's. All right, so this is, we'll call this f of x, just to familiarize us with the notation again. And let's do f of f minus 1 of x, which is the inverse, which in this case we can find by simply pretending we're solving for an equation. Can't always do that with every situation, but most functions you can. So what I'm going to do, I'm going to subtract 7. I'm going to divide by 10. I'm going to do the inverse of log base 2 of 2 to the, which is log base 2 of, I'll put that in parentheses now. I've got a division by 50, so I'll multiply by 50. And then I will add 1900. All right, so what do I see here? I see my x equals 7. The inverse of y equals 7 is right there. So that's step 1, knowing where to find the asymptote. And then I have a what? I still have a 2 to 1, right? But in this case, I'm going to, again, it's not easy to see. It's not easy to see that I'm going to multiply by 10, and I'm going to multiply by 20. All right, it's hiding there. First time I've done this video, thought about this, so thinking about it right now as in what's going on to help. Well, that's where it's coming from. All right, so let's look at the inverse of 1950, 27. So 1950, 27 becomes thinking this through here. 27. Oh, there's the 27. I'm starting at 7 and adding 20. So 27 is going to get me 1950. All right, and then this one is 40. Units of change, so they're 47. There, now I'm on top of it. Is going to get me 2000. And therefore we have 17. Looking from this now, 17 is going to get me 1900. Okay. All right. So the I guess what I'm trying to say is that the shape of a graph is the first thing you have to learn in order to get a graph drawn correct. And I think you can still use this concept that yesterday seemed to resonate nicely. You can use it in the logarithm. Just you got to look a little differently. Right, the inverse of multiplications, division. So this is where we're going to work with extending our amounts. All right, so over here, a certain amount of time gets me an amount. Over here, I'm doing it in the inverse. I'm taking the amount and I'm working backwards. So 40 divided by 10 is 4. What do you put on top of 2 to get a 4? 2 times 50, 100 plus 1900, 2000. So that's what we'll be working on in class. We'll be talking about domain. All right, just going to start talking about domain now. In other words, what numbers can I use? I can use all the values that come out of this, all the amounts, 17, 27, 47. In fact, all the amounts on this y curve are bigger than 7. Right, this is not part of the graph. This is the part you have to understand. Right, but all values are above 7. So the domain over here is your amounts, x's, have to be bigger than 7. I think we can see that they are. they're to the right of this number. And I would hope that we could see, let's make this 5. Let's make this 2.5. All right, 2.5. And 2.5 should get you what? 1850. When I add 5 to 7, when I add 2.5, which is to 7 is 9.5. We'll work decimally right now. Now let's work without decimals. 9.5 gets me 1800. And you want to put numbers in to make sure you can see how that's happening. All right, so what's 9.5 minus 7? 2.5. 2.5. And if I reduce this fraction, 2.5 divided by 10 is 1/4. 4 times that is 10. So let me put a 4th in there. And what's the exponent you put on top of 2 to get a 4th? -2. So what's happening? I'm going down 50 twice. Right? -2 times 50 minus 100 plus 1900. Right? And maybe that'll give you a better feel for this asymptotic behavior, which we haven't zeroed in on much. All right, so there's a little more of a chat about what's going on, deepen your understanding a little bit more, and we still have another 9 weeks to talk about this stuff. So we'll do one every day, talk about it, and hopefully 9 weeks from now, you'll feel very confident graphing logarithms and talking about them. The rules of logarithms are coming next.